Hello everyone, so far we have learned Pig and Hive, which are two high-level APIs built on top of MapReduce. Both Hive and Pig are the major components of the Hadoop ecosystem. With Pig and Hive, we can write parallel computing operations in very few lines to accomplish what we will write very complicatedly in the MapReduce programs. So Pig and Hive they share some similarities. They do have some differences. Hive is a declarative language. That means it's non-procedural. It specifies what to be done rather than how to do it. On the other hand, Pig is a procedural language. In Pig, it defines the flow of the data step by step. So the main users in Hive are data analysts. The Hive QL is very similar to SQL. So the SQL users can switch to the parallel computing with Hive very easily. Pig is more popular for researchers and programmers due to its more flexibility. Hive supports structured data, while Pig supports both structured and semi-structured data. Hive supports partition, like in databases, and Pig doesn't support partition. If we want to have data in small in the way that we want it to be subgrouped, we have to do that manually in the program. Hive loads data slowly. On the other hand, Pig can load data quickly compared to Hive. These are the major differences. So depend on the application, on the data, people choose Hive versus Pig. So for a lot of procedures, we can use either of them. Let's revisit the Hadoop ecosystem. It has the basic elements: HDFS, the Hadoop file system, Yarn, the resource manager, and MapReduce, the solution for parallel computing. We have learned Pig and Hive, which are built on top of MapReduce. While there are some shortcomings of MapReduce, including MapReduce forces the data process into MapReduce. It's based on the data flow from disk to disk. It's not efficient for iterative tasks and doesn't support batch processing. It doesn't support streaming data, only supports batch processing. So there are some solutions proposed to overcome the shortcomings of MapReduce. One solution is Spark. Spark is very popular nowadays. It's faster. It supports in-memory computing, so that it can work well with iterative tasks and supports streaming data. Apache Spark has emerged as the next generation big data processing engine in a very short time, and it is being applied throughout the industry faster than ever. Spark improves over Hadoop MapReduce. It is a new general framework that supports various solutions, including SQL, streaming data, complex analytics, machine learning and graph algorithms, interactive analytics, and so on. And it's much faster. It's faster than Pig, and remember that Pig is faster than Hive. It's much easier to use due to its rich APIs. Introduction to Spark. Apache Spark is a cluster computing platform. It is designed to be fast and general purpose. On the speed side, Spark extends the popular MapReduce model to efficiently support more types of computations, including interactive queries and stream processing. Speed is important in processing large datasets. When we are exploring the data, we may wait minutes or hours, depends on different solutions. Spark is designed to cover a wide range of workload that previously required separate distributed system. So it's compatible with Hadoop's HDFS, HBase, and any Hadoop storage system. One of the main features Spark offers for speed is the ability to run computations in memory. And even for the complex application run on disk, Spark is more efficient than MapReduce. And Spark is designed to be highly accessible. It offers simple APIs in Python, Java, Scala, and SQL, and rich built-in libraries. It also integrates closely with other big data tools. Spark uses memories instead of disk. Compared to Hadoop, which is mainly based on its HDFS, an operation in Hadoop with multiple iterations, it reads the data, finish the operation, and then finish the iteration 1, then write to disk. Then iteration 2 read from the disk to do its job. Even if we don't store our data explicitly in our program, it will write in temporary files on HDFS. On the other hand, Spark provides this in-memory data sharing. So during the operation with multiple iterations, the data will not be stored to disk. It will be saved in. It will be held in the memory. So in this way, it will be much faster because it avoids the data, the long time for data writing and reading from the disks, especially when we are working with large data sets. The writing and reading take a lot of resources and takes a lot of time. Okay, this shows the comparison between Hadoop MapReduce and Spark in the sorting task. The same size of data are given to Hadoop MapReduce and Spark. We can see that Spark spent much less time with much less nodes and less cores. Spark is a unified stack. It contains multiple closely integrated components. Spark is a computational engine. It is responsible for scheduling, distributing, and monitoring the applications. consisting of many computational tasks across many work machines, or a computing cluster. Because the core engine of Spark is both fast and general purpose, it powers multiple high-level components specialized for various workloads, such as SQL or machine learning. These components are designed to be interoperate closely. There are several benefits for having the tight integration. First of all the libraries and the high-level components in the stack benefit from improvements at lower layers. So if there is additional optimization in the Spark's core engine, then all the libraries will automatically speed up. Second, the costs associated with running the stack are minimized, because instead of running on the independent software systems, this platform on Spark only need to run on one. Then the deployment, maintenance, testing, support, and other procedures are not going to be separate ones. And also another advantage of the tight integration is the ability to build applications that combine different processing models. This is the Spark stack. In the following slides, we will talk about each component in detail. At the bottom level is a cluster manager. Spark is designed to efficiently scale up from one to many thousands of computer nodes. To achieve this while maximizing the flexibility, Spark can run over a variety of cluster managers, including Hadoop Yarn, Apache Mesos, and a simple cluster manager included in the Spark itself, called the standalone scheduler. So Spark can be installed on empty machine. Then the standalone scheduler will provide an easy way to get started. If you already have a Hadoop Yarn or Mesos cluster, then Spark supports these cluster managers, and your application can run on them. Okay, then on top of the resource manager is Spark Core. It contains the basic functionalities of Spark, including task scheduling, memory management, fault recovery, interactive with storage systems, and more. And it's also home to the APIs that define the resilient distributed data sets. RDDs are Spark's main programming abstraction. RDD represents a collection of items distributed across many compute nodes that can be manipulated in parallel. Spark Core provides many APIs for building and manipulating the collections. RDDs are basically data containers. Then all the different processing components in Spark share the same abstraction, called KDD. Since they share the same RDD abstraction, we can mix different kinds of transformations to create new RDDs. And the RDD is fault tolerant, like HDFS system. Okay, Spark has the SQL package. It's for working with structured data. It supports SQL and Hive query language. It supports many data sources, including Hive tables and so on. It also supports combinations with the programming data manipulations supported by RDDs, including Python, Java, and so on. And this is all within a single application. So with Spark, SQL can be combined with complex analytics. Spark Streaming is a Spark component that enables processing of live streams of data. Streaming is a concept. It means the data is continuously generated and sent simultaneously in small sizes. For example, the data stream include log files generated from production web server, or queues of message containing the status updates. So Spark Streaming provides an API for manipulating the data streams that matches the Spark's core RDD API. It makes it easy for programmers to learn the project and move between applications that manipulate data stored in memory, on disk, or arriving in real time. MLlib is a machine learning library in Spark. It provides classification, regression, clustering, and collaborative filtering. It supports model evaluation and some lower-level machine learning approaches, including the gradient descent, optimization, and so on. So with the traditional MapReduce, or even its high-level APIs on top of MapReduce, it is because they don't have the in-memory computation supported. So with those approaches, it will be really difficult or even impossible for some machine learning algorithms to be applied. And right now, with big data and the high demand of machine learning algorithm trained on big data, Spark is this is one of the reasons that Spark getting very, very popular right now. So it can do machine learning that the MapReduce based system cannot do. GraphX is a graph library in Spark. The graph can be a social network graph, and the GraphX performs the graph parallel computations. It's like the other applications on Spark. The GraphX extends the Spark RDD API, and it supports creating the graph and supports operators for manipulating the graphs, and a library of common graph algorithms like PageRank and triangle counting. Okay, about Spark. It is new. It's started in 2009 as a research project in the UC Berkeley RAB lab. The researchers in this lab had previously working on Hadoop MapReduce, and they found out that MapReduce was inefficient for iterative and interactive computing jobs. So from the beginning, Spark was designed to be fast and iterative. Then it brings the idea for support for in-memory storage and efficient fault recovery. And then the Spark's users, they use Spark to monitor and predict the traffic congestions in the Bay Area. Then more and more organizations begin to use Spark and getting more and more popular. And in 2011, the AMP lab started to develop higher level components on Spark. Spark can naturally support any data from HDFS and all supported by Hadoop APIs. And Spark supports any input format for Hadoop. On the other hand, it simply supports for Hadoop, but it doesn't require Hadoop, so it's more flexible than Hadoop.